We back. Day two. Programming every day until I get good or until I find a job or something. Um, yeah. Let's just get straight into it. Um, Back to the Leetcode website. So I kind of looked at this roadmap a little bit. I think I'm gonna do linked list question. I don't know if we did one yesterday. No, that was a few days ago. I did one. So I've been kind of going through the linked list ones. I think we're gonna do, since I've already done these ones, I guess we'll just go to. I mean, we looked at this one. This one looked kind of confusing. I didn't even know. I think this is a. We might. Yeah, maybe we'll look at this one a little later. For now, but we're gonna go to this one. What was it called? Find the duplicate number. Okay. Find the duplicate number. Okay. Given an array of integers and nums containing n plus 1 integers where each integer is in the range 1 to n inclusive. There's only one repeated number in nums. Turn this repeated number. Must solve the problem without modifying the array of nums and using only constant extra space. I don't know what that means, to be honest. Extra space. Okay. So does that mean I can't create? That means I. Constant extra space. Okay. So I think that means that you can't. I'm just gonna solve this. I think it's like this, right, or something. I'm just gonna solve it using a dictionary really quick just to see. I think extra space is talking about like I can't create a dictionary or something like that, but to be honest, I'm not really 100% sure. So we can do answer is equal to 0, and we want to loop through I in nums, and then if I in my dick, and we want to just add. Wait. Equal to 1. We can just add the count. And we want to do this statement if my I greater than 1, then we can just return yeah. Answer is equal to answer is equal to I, right? Yeah. I'm gonna break out of this loop. Doing else. And we just want to return our answer. is going on here? Here too. Okay. Okay, so that worked. Ah, I accepted it. I thought it was meant to be a linked list problem. Isn't it? Like what? I guess no one is really using a linked list. I thought it was meant to be a linked list problem. Let's take a look, actually. Let's take a look. Oh my gosh.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve find the duplicate number. And you can see that I'm not really a big fan of this problem, and maybe I'm just salty, but I really feel like this type of problem is the ultimate test of whether you've seen the problem or not. But I'm still solving it nonetheless because it's an interesting problem, and it does show up in interviews quite a lot, it seems. I really don't know how anyone would be able to solve this problem in a 30-minute interview without having seen it. Even the person who came up with the algorithm, Floyd, I doubt even he could solve this in 30 minutes in an interview setting. But that's okay, let's just learn the problem today. So we're given an integer array of nums containing n plus 1 integers. This is the length of the array, but every single value in the array is going to be within the range 1 through n. So we have n different values that could be in the array, like n different choices for the integers, but we have n plus 1 integers. So that kind of implies that at least one of the numbers is going to be repeated, and they tell us that actually it's only one number is guaranteed to be repeated. And the only thing we want to do is return the number that is repeated more than once. Now, the easy way to solve this problem, of course, would just be have a hash set, right? Iterate through every single value, find the one that occurs twice by using our hash set. That's going to be O of n time and O of n memory, but they tell us that we can only use constant extra space, and we can't even modify the input array, so we can't even sort it or anything. And I think those restrictions probably make this a hard problem rather than a medium problem, but that's okay. So there's two aspects to this problem, and I'm going to explain both of them. So we're going to solve this in O of n time and O of 1 space. The first thing to recognize is this is a linked list problem, specifically a linked list cycle problem. And the second thing is to know Floyd's algorithm, which will tell you the beginning of a cycle in a linked list. So there's two problems: one, to even recognize that this is a linked list problem, and two, to know the algorithm to actually apply to it once you know that. So let me actually show you how we can figure out both of these things. And yeah, you're right, it's probably not super intuitive, and I'm not really sure how you would be able to figure it out on your own if you've never done something like this before. So remember that the length of our array is n plus 1, but every value in the array is going to be between 1 and n. So there's n different values, but there's n plus 1 positions. So in this array, we have 5 different elements, right? And we know that the elements are going to be in the range 1 through 4, right? So basically, if instead of thinking of these as values, let's think of them as pointers. So we know for sure that every single value in the array is going to be in the range 1 through 4. That means if we considered every value as a pointer, each value is going to point at some position in this block of 4, you can see that this one points at position 1, this 3 points at position 3, this 2 points at position 2 over here, and this 4 points at position 4 over here, and then this 2 points back at position 4. So that's how you can kind of see that, in that case there was a cycle, and you can see I basically drew out the linked list version of that. So it's not hard to see that this portion is going to form a cycle, because no matter what value we look at, it's going to point at some other value inside of this range. There's never going to be an exit condition. None of these values are going to point outside of the range, either over here or over here. None of them are going to point outside of the range, so this portion is going to form a cycle linked list somewhere, right? What about this value? Is this going to be a part of the cycle? Notice how none of these values, nothing is ever going to point at index 0, because remember, our range is between 1 through 4. None of them is going to be 0, so none of them is going to point here. So we can guarantee that this is not going to be a part of the cycle. And when you see I took this array, drew it as a linked list, you can see this is index 0, right? You can see that this was our cycle portion, but this was not included in the cycle. And that's going to be very important, because when we start traversing this linked list, we're always going to start here, because we know this is not a part of the cycle. So in our input array, you can see that 2 is the duplicate, right? 2 is the one that shows up multiple times. So in the context of this problem, this position is going to point at index 2, and this position is going to also point at index 2. So what does that tell us about our linked list? That means at the node that's labeled 2, each value of the node, each label is going to map to the index. So this is basically node 2, right? What that tells us about node 2 is that multiple nodes are going to be pointing to node 2, right? Therefore, we know that this is the one that's going to be the start of the cycle. We know for sure there's going to be a cycle, and we know for sure there's going to be a portion before the cycle. The portion before the cycle, of course, is eventually going to lead us to here, which is the start of the cycle. And of course, there's going to be another node that completes the cycle, right? Pointing back to this node. So if we can somehow identify the beginning of a cycle in this linked list, then we will know that that beginning of the cycle is the return value that we're looking for in the output. You can see, yes, 2 is the duplicate. That's the one we want to return. Therefore, we want to return the start of the cycle. So at this point, it's all about applying Floyd's algorithm to find the beginning of a cycle. So that's, once you've determined that it's a linked list problem, then you just need to apply this algorithm, and this algorithm itself is actually also not very intuitive. So let's look at a slightly different example so I can illustrate the Floyd's algorithm. So first I'm just going to tell you what the algorithm is, and then I'm going to explain a little bit of the intuition of why it actually works. So the slow pointer and fast pointer are both going to start at this position. The slow pointer, of course, is going to be shifted by 1 each iteration. So that's 1 jump, that's 2 jumps, that's 3 jumps. So we just made 3 jumps with our slow pointer. Let's do the exact same thing with our fast pointer. So remember, a jump with the fast pointer is going to be 2 positions. So that's 1 jump, that's 2 jumps. And let's make 2 more jumps from here. So we're going to go to 2 and then back to 3. So you can see that it got a little bit messy, but we made 3 jumps with the fast pointer and we made 3 jumps with the slow pointer. And you can see this is the first position that they intersected at. So this was the intersection of the 2 pointers, right? This was the first intersection. So that's the first phase of this algorithm. First, we find the first position that they intersect at. Then we take our slow pointer, leave it here. So our slow pointer is going to be here, right? And then we're going to be done with the fast pointer. We're going to take a second slow pointer and put it right at the beginning of the array. And each of these slow pointers, we're going to keep shifting them by 1 until they intersect 1 more time. So this slow pointer is going to be shifted by 1. This slow pointer is also going to be shifted by 1. Hey, we just found out that they intersected, right? And this second point of intersection is always going to be the result. It's not intuitive at all why this is the case yet, but let me explain that. But now you know the algorithm. If all you wanted to do was memorize it, that's literally it. Now you can code it up. That's why I don't like this problem, because it's simple if you've solved it before. So this algorithm relies on the fact that the intersection point, like the first intersection between the 2 pointers, the distance between this point and the beginning of the cycle, which in this case is 1, right, is always going to be the same as the starting point distance from the cycle, from the start of the cycle. That's also 1, right? Since we know that's the case, that's how we can take 2 slow pointers, start one here, and then keep shifting until they intersect. Then we get the result. But why is it the case that the distance between this is the same as the distance between this? Looking at this bigger example, why is it that the distance between the start and to the start of the cycle is always going to be the same between the intersection and the start of the cycle? Why is that the case? Well, let's just draw out a few distances. Let's say the distance, this is P, right? Basically, P is the number of previous nodes we have before the actual start of the cycle. And let's just say, arbitrarily, this is the intersection point between the 2 points, right? And we don't know that this is going to be the same, so let's just label it X for now. Let's not label it P, because we don't know for sure that it's going to be the same. Let's label it X. This is our unknown. And then the remaining portion of the cycle is going to be C, which is the length of the cycle, right? In this case, it's 5, minus X, right? Because the total cycle is 5, which is C, and this X portion makes up the remaining portion of the cycle. That's why this part is C minus X. So we know that the slow pointer is going to start at the beginning, it's going to traverse this P portion, and then it's going to traverse this C minus X portion, and it's going to land at the intersection point, right? Now we know that the fast pointer is going to do more than that. It's going to, of course, do this P portion once, then it's going to do a complete loop, right? Because remember, the fast pointer is going to outloop the slow pointer, and it's going to overlap the slow pointer, so it's going to have to complete a full, at least one full loop, and then once it does a full loop, it's going to be back here, and then it's going to traverse this C minus X portion to get to the intersection point, right? We don't know where the intersection is. Obviously, I drew it over here, but it could be anywhere, so let's write that mathematical equation out. So we know that 2 times the number of iterations the slow pointer does is equal to the number of iterations the fast pointer does, right? How many spaces it moves versus how many spaces the slow pointer moves. Of course, the fast one is twice as fast.
I definitely learned this in college.
Multiply the slow one by 2 to make it equal to this one. And how many iterations did we say that the fast one does? It's going to do P plus CX, right, to get to this position, and then it's going to do another complete cycle starting from here to get back to this position, right? So the fast pointer is going to be P plus C minus X plus C again. So more simplified, it's going to be P plus 2C minus X. The slow pointer is just going to do P, and then it's just going to do C minus X. So we'll have a 2 on the outside, P plus C minus X. So I'm going to take this equation and simplify it over here to the right. So once we simplify it a little bit, we're going to get 2P plus 2C minus 2X, which is equal to P plus 2C minus X. And then this is the part where you can start doing a little bit of algebra. So we can cross out the 2C from both sides of the equation. We can cross out from each.
I'm so lost already.
This algorithm, we're going to have 2 finally pointers, fast and slow. They're always going to start at 0, remember, because we know 0 is not a part of the cycle. That's for sure. And we're going to keep iterating through these loops. I think there's an easier way to write this code, but I'm lazy, so just while true. We're going to, and we start out with while true because we want to keep going until they intersect, but notice how they already intersect at the beginning. So we're going to update slow, so basically slow is going to be set to whatever it points at, so nums of slow, right? And then fast is going to be the opposite, or the same thing, nums of fast, but remember we're advancing fast twice, and So we can just do this. And of course, fast and slow are always going to be in bounds, right? They're never going to point out of bounds. We know that for sure based on the restrictions that we're given. And if slow is equal to fast, that's when we can break out of the loop. If they're not equal, then we're not going to break. This is basically a do-while loop, but I don't think you can do that in Python. So once we've done this, that's how we know, okay, fast and slow intersected here. So now we're going to create a second slow pointer, slow2. We're going to set it to the beginning, right, back at index 0. And now we're going to keep incrementing this slow pointer and the first slow pointer until they intersect. So this is phase 2 of the algorithm. While true, advance the slow pointer by 1. And advance the second slow pointer by 1 as well. Notice how trivial this code is. The hard part is just figuring it out. So, and we're going to keep going until they intersect. So if these were equal, then we can break out of this loop and then return the slow pointer, right? We can return either of them, slow 1 or slow 2. Index that they're at, right? Slow 1 and slow 2 are always an index, and the index that they're at is the duplicate number because we have multiple values pointing to the same value. That's the duplicate. We can actually take this and return it here. So I'm just going to go ahead and do that, and this is the entire solution. Okay, I don't know what I was thinking. I don't know why I put fast on the outside. This is nums of fast, which is a number, which is a different index, and then we're going to use that same index again in the nums array. That's how we're basically advancing fast by 2. We could obviously write it in different lines of code, but I'm just going to leave it as it is just because it's a little bit neater. And also, I don't really know what I'm thinking, but the second slow pointer also needs to be advanced. I don't know why I called it slow 1, but that is the entire code. And then once they finally meet, we are going to be returning that index. And as you can see, the solution does work. It's a linear time solution. We definitely didn't need to use any extra space. We didn't need to modify the input array. This is the Floyd's algorithm. With a fast and slow pointer, beginning of a cycle detection. So I hope that this was helpful. If it was, +1 position.
I'm still kind of confused, to be honest.
So in this array,
This is what we did. False. Curious.
true, we're going to, and we start out with while
Oh, sure. We want to make L equal to I. What was it, like nums plus I or something? I don't remember.
Points the opposite, and so nums of fast. But remember, we're advancing fast twice, and so we can just do this. And of course, fast and slow are always going to be in bounds, right? They're never going to point out of bounds. We know that for sure based on the restrictions that we're given. And
So is equal to I'm slow. Why did I do I? Jesus. This is equal to fast. I don't. To be honest, I have no idea what this is doing. This what is it? Fast times fast. I don't get that. I gotta look at the video again.
Going to be between 1 and n. So there's n different values, but there's n plus 1 positions. So in this array, we have 5 different elements, right? And we know that the elements are going to be in the range 1 through 4, right? So basically, if instead of thinking of these as values, let's think of them as pointers. So we know for sure that every single value in the array is going to be in the range 1 through 4. That means if we considered every value as a pointer, each value is going to point at some position in this block of 4. You can see that this one points at position 1, this 3 points at position 3, this 2 points. Each value is going to point at some position in this block of 4. You can see that this one points at position 1, this 3 points at position 3, this 2 points at position 2 over here, and this 4 points at position 4 over here, and then this 2 points back at position 4. So that's how you can kind of see that, you know, in that case there was a cycle, and you can see I basically drew out the linked list version of that.
Position.
So it's not hard to see that this portion is going to form a cycle, because no matter what value we look at, it's going to point at some other value inside of this range. There's never going to be an exit condition. None of these values are going to point outside of the range, either, you know, over here or over here. None of them are going to point outside of the range. So this portion is going to form a cycle linked list somewhere, right? What about this value? Is this going to be a part of the cycle? Notice how none of these values, nothing is ever going to point at index 0, because remember, our range is between 1 through 4. None of them is going to be 0, so none of them is going to point here.
we want to create a new pointer, right? Called slow2. Right, and then if slow2 is equal to nums. Fuck, I don't even remember what it was. I think it's actually the slow pointer. Isn't it or something? I don't know. Can't really remember. To be honest. Yeah, I don't even remember. What is it?
So we can guarantee
I think I
this is
understand it now.
not going to be a part of
They're gonna meet, right?
itself is actually
I need to see the second
these are
part.
going to be x, right? Because the total cycle is 5, which is c, and this x portion makes up the remaining portion of the cycle. That's why this part is on this. That's how we know, okay, fast and slow now. So this, notice how trivial this code is. The hard part is just figuring it out. So, and we're going to keep going until they intersect. So if these were equal, then we can break out of this loop and then return the slow pointer, right? We can return either.
The fuck did I do wrong, dude? Int object is not scriptable. What the hell does that mean? Jesus, what am I doing wrong here? Syntax error. Oh shit, yeah, at the end of the video. That's why I hate reading other people's stuff. Why is it taking so long? Time limit exceeded. That's a really interesting algorithm. I would never thought about that. What did this guy do? Where does he go like those array? A new array. I know, right? What the hell is going on here? I don't even understand the solution. I'm just curious, like. This is really hard to understand. I understand this now, but it's like kind of similar to the. It's kind of similar, like it's using. If I is equal to 3, right there you. That's interesting. I don't know. All right, that gave me kind of a brain explosion. Let's do another one. We did this one yesterday. Oh my gosh, I have a headache now after that. School's trying to take an idea for students. Give it an array heights represent. I'm really bad at reading questions, by the way. Like, school is trying to take an annual photo of all the students. Stand in a single file line in non-descending order. Let this ordering be represented by the integer expected, where expected I is the expected height of the ith student in line. You are given an integer array heights representing the current order that the students are standing in. Each highest I is the height of the ith student in the line. Turn the number of indices by highest I is not equal. Okay, so this way that we can is it sorted? I don't even know, dude. Wait, what? Aren't we given expected? Wait, what? Oh. Wait. Oh, okay, we're meant to sort it. Oh, okay. We gotta sort it. Oh, okay. So we just gotta sort the array, return the height. Or else we return the wrong positions, I think. I think we can kind of cheat in this, to be honest. I think there's a way in Python that you can just sort an array. Like, what is it? Dot sorted in Python, I think. What is that? That's sorted do in Python. Okay. Let's try this. So we're given heights, so let's make a copy. So let's do shit, how do you copy an array in Python? Isn't there an easy way? Copy copy method. Let's do expected is equal to heights dot copy, right? That's how you do it. Yeah. And let's print heights and print expected. Probably a better way that you want to do is actually dude. I guess we can slice too, can't we? Heights and then we can slice like that. Okay, I think that worked. Okay, sweet. Alright, I guess we can cheat and just do expected dot sorted. Right? Is that how it works? How to use sorted function in Python. Go to is equal to sorted expected. In range nums. If nums I think you can't. I think this is Python 3. I don't think this is gonna work, but okay. Expected 2 I. Let's just. What do we return? Oh, we want to. Oh, okay, we want to count. Okay, that's count variable. And we just if it's not, we increment the count. Else we just continue, and we just want to return our count. Oh shit. That's what I meant. Whoops. God, I'm so used to it being nums. Heights high. Okay, there's. Okay, I'm not satisfied with that solution. That's cheating. What's. I guess we can search out like. What's the fastest way to sort array? There must be a faster way to do it, dude. Hold up. I don't want to check it. I'm just gonna check it. Fuck it. Oh, they did the same thing as me. What? Oh, it's because I'm going through and I'm slicing it. That's why. I mean, I didn't even need to do that. I can just do expected is equal to sorted heights. Expected to is not defined. Okay, maybe that'll be faster. Yep. Okay. Oh. All right. Nice. 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 That one was too easy. We're gonna do another one. Combination sum. What is this? For some reason I was just like viewing it in Python better. Have I solved this one? No. Given an array of distinct integers, candidate and target. Should target return a list of unique combinations of candidates with the chosen numbers sum up to target combinations in any order. I swear I've done combination something. Sum 2. No, I haven't done this one. I swear I did a problem that was similar to this. Okay. Array of distinct integers, candidates, and a target number. Target. Return a list of all unique combinations of candidates with the chosen numbers sum to target. Return the combinations in any order. Hmm. Two or three candidates, T2. What's the best way to approach this? That's what I was thinking, backtracking. I'm not good with recursion, to be honest. That's what I gotta get better at. I gotta get better at recursion. I'm thinking. Backtracking in Python. Getting tired. Okay, so gotta think about the way we want to do this. We want to check this number. So we're gonna look through, check this number. Is it sorted or sort? I can't even remember. I think it's sort. Bro, what? Did I spell it wrong? Oh my gosh. Why is this working? What was it before? I don't even know. Is it dot sorted? Or, yeah, it's sorted. No attribute sorted. What? Wait, what, bro? Oh, I think it's candidates. Is that it? I don't even remember. Okay. Okay. So to begin with, for in new candidates, yes, in new, for I in range, length, new candidates. We want to check if new candidates I is greater than target. Because if it is, check if new candidates I is greater than target, we can just break. Because technically, if it's bigger, then there's no point of keep looping, right? I haven't done DFS or anything like that, so I got no idea. Create an array found. Okay.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve combination sum. And
I haven't done a lot of DFS or things like that, so I don't really know kind of where to start off the top of my head. But
this is another problem from that line 75 list. The link will be in the description. So we are doing one more problem and have very few problems from this list remaining. So we're given an array of distinct integers called candidates, and we're given a target integer called target, and we just want to return a list of all the unique combinations of candidates where all those numbers end up summing to the target value. And we're allowed to return those combinations in any order, and we're also allowed to use the same number from candidates multiple times, but we don't want to have duplicate combinations. For example, if 2, 2, 3 sums up to 7, right? That means 3, 2, 2. These are the exact same values, right? Just in a different
Swear to God, I've done this one before, but I can't remember.
order, these sum to 7 as well. So we don't want to add both of these combinations to the result because they're the exact same. So what we're saying is we want combinations, we don't want permutations that end up summing to the target value. So in this example, you can see that we are given these candidates and a target of 7, and we have 2 different ways that we can sum up to 7. Of course, 7 by itself does sum up to the target, and 2 occurrences of the 2 value and 1 occurrence of the 3 value added together are going to lead to 7 as well. So then we return these 2 combinations as our result. So I would say the difficult part about this problem is trying to figure out how to eliminate duplicate combinations, right? For example, if we just brute force it like a decision tree, so we have 4 different values we can choose each of them an unlimited number of times. What we can do is have 4 decisions in our decision tree, right? Like that might be the naive thing that you start with. So we would get 2, 3, 6, and 7, and then we'd basically continue that, right? On one path over here, we would find, okay, we found the 7, so we found the target, right? So we found one way that we can reach the target. So therefore, we don't need to continue down here because as we add more numbers, all of these values are going to be positive. So as we add more numbers, we're only going to get a sum larger than the target. So, you know, I think it's kind of obvious why we don't continue down this path, right? But down here from the 6, let's try to continue, right? We can add a 2, so we'd get 6, 2. We could add a 3, so we'd get a 6, 3. We could add another 6, so we'd get 6, 6, and we could add a 7 where we'd get 6, 7. So notice how all of these are going to sum to a value greater than the target. So down this path, we never ended up reaching the target. We only went over the target, so we don't continue down any of these paths, right? But now let's continue down this path. So here we can get another 2, we can get a 3, we could get a 2, 6, but in that case we would get 8, which goes over our target. We could also get a 7, 2, 7, but that also goes over our target. Now here's the part where we're going to end up getting duplicates. So I'm going to show you why this type of decision tree does not work. So here we could get a 3, for example, right? So we'd get 2, 2, 3. Now that sums to the target. Down this path we could choose a 2, so we'd get 2, 3, 2. Notice how both of these end up summing to 7, but they're the exact same. They're just in a different order. We have 2 2s and a 3. Here we also have 2 2s and a 3. So we ended up getting the same one twice. So this works in finding the combinations, but we end up getting duplicate combinations. So what kind of decision tree can we try that gets us the result that we want, but does not have these duplicates? Let me show you how we're going to do that. Let's logically think about this. We know that we have one value in our candidates, 2, right? So we can try to get all combinations that include this 2 value, right? And see if any of those combinations leads us to the target value 7. Now, we could also... So then if we make a second decision over here, right, in this decision, we're definitely including at least 1, 2. Now, if we go down this path, we want to make sure that none of the combinations down this path ever match the combinations down this path. How can we guarantee that? Well, in this side, we said we're definitely including at least 1, 2. How about in this side, we don't include even a single 2? So basically, we skip 2. So here we're going to have an empty array because we skipped the 2, right? All we said is we were able to start from here, but we said no, we're just not including a 2. We're just going to do combinations with these 3 values. That's going to guarantee that none of the combinations on both sides are going to be matching. And that's basically the logic that we're going to follow. So from here, remember, we can include multiple 2s if we want to, right? So one decision here could be including a second 2. So we get 2, 2. Now, this path is going to include all combinations that include at least 2 2s, right? But remember, our definition for this decision tree needs to be recursive, right? Because we don't want any of the combinations down this path to be the same as any of the combinations down this path. So what we said here is we're going to include 2 2s. How about down this path? We say that we're not including any more 2s now. What we're saying is we had 1 2, but now we're done. We're skipping 2s. Now we're only going to use values from here. So that's the recursive thing, right? We're basically doing the same same decision down here as we did up here. So here we're going to say we ended up skipping the 2, and we still only have one single 2. And so let's just continue to repeat that. So over here, we're going to add another 2. So we'll have 2, 2, 2. And over here, we'll say, okay, now we're done with 2s, right? Where we're going to keep ourselves at a limit of 2 occurrences of 2. And we're basically going to continue this logic until we get to our base case. So over here, you're going to see if we ended up having 4 2s, we'll get a target of 8. So therefore, we went over our target value. So we're going to stop. But down here, right, this was our path where we said, okay, we're not going to include any more 2s in this path. So here we can make a decision. We can add a 3. So then we'd get 2, 2, 3. So we're continuing that recursive definition. And so notice how we have 2, 2, 3, that's 7, so we did find at least one combination. But remember down now, if we make a decision to the right, we want to make sure we don't have any duplicates from here. So in this side, we decided to add 1, 3. How about down this path, we say we're done adding 3s. We're not even going to add a single extra 3. So this is going to remain as 2, 2. Now, I think it's pretty obvious that down here, since we're only allowed to add values 6 and 7, neither of these is going to end up leading to the target. If we add a 6, we'll get a total of 10. If we add a 7, we'll get a total of 11. Neither of these, both of these go over our target. So let's quickly run through the rest of the decision tree. So over here we said we added a second 2. So over here, we're not going to be adding any more 2s. So here we can add a 3. So we'd get 2, 3. And over here, we would skip adding 3s, right? So we're not going to add any more 3s. This is going to remain as 2. Now down this path, at this point we have a total of 5, so we're only allowed to add values 3, 6, or 7. All of those are going to end up leading to a total of greater than 7, so we won't be able to find any solutions down this path. I'm just skipping our result variable, which is basically going to be the target value. That's going to be the big O and big O time complexity of this problem. So we are going to do this recursively, but let's have our result variable, which is basically going to be global for the scope of this problem, because I'm going to define a depth first search function inside of our outer function. So a few variables we're going to pass into here. We do want to maintain which of the candidates we're still allowed to choose. So like I said, we're going to have a pointer I that's going to determine that. We're also going to have a current variable. We're only going to have a single occurrence of this. It's just going to be a list that tells us what values we have added so far to the current combination. For example, like we could have 2, we could have 2, 2, right? 2, 2, 3, etc., etc. And for the values in our current combination, we do want to have a total, so we want to be maintaining what's the total sum of those, because if it ever reaches our target sum, then we know we have found a solution. If we ever go over our target sum, that means we've reached the base case and we can't continue anymore. So in our DFS function, let's go ahead and define those base cases. We know the base case is if total ever ends up reaching target, that means we found the result. So what we're going to do is result.append. We want to append the actual combination, so we're going to append current. And since we're only maintaining a single variable list for current, we don't want to actually append current itself. We want to create a copy of it, because we're going to continue to use this current variable when we're doing the other combinations recursively. So we don't, because then we're going to be modifying it. So we just want to create a single copy before we actually add it to the result. And after we're done with that, we don't want to continue the rest of this function, so we're just going to go ahead and break out of it by returning. So that's the base case where we succeed. What's the base cases if we end up being impossible to find a combination? Well, one is going to be if I is out of bounds, meaning we can't choose any more candidates. So if I is greater than or equal to candidates, or our total ended up going over the target that we're trying to reach, that's a base case where we have to return immediately because we cannot find a combination then. Now for the actual recursive step, remember we have two decisions to make. We can choose to include the value at candidates of I, right? We can choose to include this value. So what are we going to do if we're including this value? Well, first of all, we're going to take our current values that are in our combination. We're going to take that candidate and go ahead and append it to our current combination, right? We're going to do that before we end up actually calling our DFS function. So we're going to call DFS, and what are we going to pass in? Well, we're including this candidate so we can potentially continue to include it, right? So what we're going to say for our index I that we're passing in is I stays the same, right? We're not restricting which candidates we're allowed to choose from just yet. So I stays the same. We pass in current, because we just updated it right now, so we can go ahead and pass it in. And the total did end up changing, so we took our current total and added this candidate to it, right? So we can go ahead and pass in total plus candidates of I. So let me delete this line because we're not doing anything with it. But yeah, so this is going to be that first decision where we do include the candidate. Now the next decision is going to be where we can't include it, but after we called this function, we want to clean up a little bit. We ended up adding this value.
Do they have DFS on here? Hey, it's here. I have to refresh myself with trees and everything.
Candidates, our current combination. So we want to go ahead and pop that before we go down the other decision. And so once we pop that, we can go down the other decision. That's if we're not ever going to include this candidate. So for the index, we're going to pass an I plus 1, indicating that we can't include any occurrences of I. And for current, we can just go ahead and pass in our current combination, and total is going to stay the same because we didn't end up adding any value to it, right? We left our current combination as the same as it was before when we actually called this function. And once that's done, we've basically made our two decisions, right? Can you see what's going on? Can you see that we called depth first search once, and then we called it a second time? So we did create that two branch decision. And after we're done with that, we can go ahead and return. And in this case, we actually don't need to return. So that is the entire DFS function. Last but not least, what we want to do is actually call it out here. So we're going to call it, passing in 0 as the beginning index, passing in an empty array as the current combination, and passing in 0 as the current total. And then once that is done, we will have updated our result, which we declared up here, and then we can simply go ahead and return that result. It should contain all of the combinations that end up totaling to the target. So you can see this problem isn't too bad to code. This backtracking approach isn't too bad once you kind of understand the two decisions that we're actually making. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Alright, we're gonna come back to this. Come back to that later. We're gonna work a little bit on this website. Oh, not this. Let me disconnect from this VPN. Where is this? Dude, what? I can work a little bit on my website, a little bit. Portfolio. Trying to add a I don't like the distance here. I'm gonna add a little video here. That's what I want to do. section, profile, about. Let's do video tag, okay. Profile picture assets. Let's create a new div class here. Call it podcast. How do you add a video in HTML? I don't know if this is. We want to create a little source here. Make this. Now we gotta find a video on YouTube. Jeez, this might take a little while. Podcast. Fraternity podcast.
That was my first semester here at EIU, and obviously that was.
Like that owl, baby. Like that owl. Maybe we're gonna have to use iframe. YouTube loop, YouTube, playing a YouTube video in HTML. Oh. This is for a downloaded video, whoops. Iframe. Width is equal to 500. Height is equal to 400. SSC is equal to, paste our link. And we paste our link. Close with our iframe. Looks good. Fuse to connect. I don't know what that means. Fuse to connect. find the link to embed. Where is the share? Just got here, share, embedded. Oh, here we go. Oh wow, it just gives me the code. That's cool. Oh, I want to fix that. Yeah, baby. Now we gotta create some CSS. Oh, dude, my ear like hurts so bad. Can't remember how to do this. File section, icons, title. Well, isn't this meant to... this, dude, to be honest. Like, my gosh, dude. To be honest, man, I have no idea where I even want to put this. Like, how I kind of want this to look. I'm so like uncreative. Maybe should I? Maybe just move it here or something. Maybe just move it down a bit. I would think. Let's go put it down in the about section, actually. Let's put it right next to this. I have the worst headache right now. Oh my gosh. Alright. Starting to get a headache. I think I'm going to end it there. Peace.